Hey guys, welcome to the first lab. Again, my name is Max. So I know it's online, it's not ideal, but I'll try and keep it as short and sweet as I can make it. So for the first lab, as per the course outline, we're going to do specific gravity of soils. Moisture content is also on there, but it's going to be built into the lab, so you're only going to write the one report for the specific gravity of soil solids. What I also have in there is the specific gravity of coarse aggregate. The reason I have that in there is because it'll give you a little bit better idea of how this procedure works, but it is not a mandatory lab test. So I'll be running through both of them, but the specific gravity of coarse aggregate is extra credit. The two procedures, the background to all of them, the way it all works is basically identical. The actual procedure of how we're going to do it is slightly different. The calculations are basically all the same. So if you want to do that, it'll be a lot of copy and paste for the bulk of the lab report. It'll just be, new numbers and, a slightly different application. So obviously, I'm not on campus right now. Strata has let me, or has given me permission to do all the labs here. So, this is a lot of what I do for work, actually, working with construction companies, working with the state, working with different clients for all the material testing needs. So I figured, give a little more real life application doing it here, doing it the way that we do things. So, specific gravity. Specific gravity is a unitless value that you use for looking at unit weights and densities. The way that it actually works is that you standardize a unit weight comparatively to the unit weight of water at a certain temperature. The convention standard, is 20 degrees Celsius. So we'll be basically dividing out everything for a unitless value in comparatively to water at 20 degrees Celsius. So the way that it would work is when you have your specific gravity, which I'm going to say, or denote as GSP, to be some value. Typically it's 2 point something. Let's call it 2.650. Then all you'd have to do, if this is your specific gravity for a soil sample or maybe for concrete or for whatever it may be, you multiply it by the unit weight of water. And if this was in pounds per cubic foot, then you get a variable out in pounds per cubic foot, so then you'd use it in all your estimating and whatever else that you happen to need a unit weight for. So that's this is basically what we're doing. The lab itself is to calculate this variable. So the lab procedures for specific gravity of soils and specific gravity of fine aggregate are very similar. The key difference there is going to be fine aggregate versus soils, which is basically just grain size distribution. So fine aggregate is going to be a little bit coarser than your soils would be, but because it's very similar, I'm not gonna, I'm kind of going to use those two names interchangeably. In reality, they're not, but for our purposes right now, they will be. The lab is specific gravity of soils, but I will be using a fine aggregate because that's the sample I have available to me right now. For aggregate, that's basically just going to be larger particles of rock, basically anything from the number 4 sieve size up. And you guys should have covered that in lecture already. So far, as at least from my knowledge of looking at your guys' lecture slides, everything that we're going to cover in lab, you guys have already gone over. So none of the calculations, nothing that we're going to do in the lab in total should be a surprise to you guys. Everything should be covered in basic soil mechanics. So if you look at the folder that I've uploaded in your in the assignments file, it'll be a zip file. So just unzip that, and you'll have a bunch of documents. The documents that I have posted are the lab manual for one of what this lab should be, and I will be using that as kind of the main procedure. But I've also uploaded all the AASHTOs and ASTMs that are relevant that I can find that I have handy to me. So the AASHTOs and ASTMs, those are the actual standards that are used in industry. The lab manual is based off of the ASTM, but the ASTMs and AASHTOs are what we use here at Strata, what MTI would use, what All West would use, basically any what any firm would use as a standard. The difference between them is AASHTO is adopted by US DOT and is going to be basically only for highway construction, whereas ASTM is a little bit more versatile, and the extent of the ASTM standards is significantly larger. AASHTO is basically only for different types of roadway construction. So the actual procedure of what we're going to do is I'm going to take, for the soils, I'm going to take a volumetric flask, I'm going to fill it up full of water, we're going to get that temperature, and I'm going to take my soil at what's called SSD, or saturated surface dry, and we're going to put it into the flask. We're going to take different mass measurements, so what we're ultimately trying to get to, what the specific gravity here is the mass of solids or mass of soil over, not equal mass, it would be equal, squeeze by it, just double check I don't mess this up. It would be mass of equal volume of water. Remember, so the actual equation that we're going to be using is going to be our MS, which is going to be our mass of solids. This is dry, divided by what we're going to call MW, and MW is going to be the mass, this mass of equal volume of water, which is we're going to call M1 plus MS minus M2. So M1 is going to be the mass of the flask filled up to exactly, I can't remember if it's 500 or 1,000 milliliters of water. MS is the same value. M2 is the two of them together. So I'm going to dump out some water out of the flask. I'm going to add my soils in there. We're going to go through our de-airing procedure, and then we're going to fill it back up to that same quantity of that same total volume. So the volume in total isn't going to change, but what's in that volume is, and that's how we're going to come up with this mass of equal volume. So that's how this equation is going to work. Now, it's for the coarse aggregate, it's basically exactly the same. It's just a matter of how we get this is going to be slightly different. Okay. For the coarse aggregate, there is one other value that you're going to need to calculate. That's going to be in your end result, and that is absorption. You can abbreviate ABS. Absorption, we're not going to get it for soils. There is an absorption there, but what we're really looking for, and it's significantly higher in coarse aggregate. And the reason we look for it is if you have absorption when you're doing a concrete mix design maybe, or if you're trying to add an exact amount of water to a substrate or whatever it is that you guys are trying to do, if you want to have 10% moisture in your sample, you need to add an additional amount that's going to be directly proportional to your absorption, because that's what the rock is going to suck up, right? That's the moisture you're going to lose. If you're doing a concrete mix design and you want a specific value for your water cement ratio, you need to add extra water for the absorption, because that extra water is going to be sucked up by aggregate and it won't actually be able to react with your cement. The absorption is going to be a value that we're going to calculate at SSD. So it's going to be your SSD mass, again, a saturated surface dry, minus our dry rock divided by our dry rock times 100%. So if you do the extra credit for that extra lab, this is a value that I'm going to want to see in your results. And again, it's not like these equations are super cumbersome or long. The only other thing that's going to be in there that you guys are going to need to know is how to calculate moisture content. So your moisture content, all that is your moisture in your sample divided by your dry sample, which you do by saying your wet minus dry over dry times 100%. Now, if you look at the raw data sheet that I gave you guys, I do not have the dry weight of the sample I used for the fine aggregate / soils specific gravity. The reason for that is I needed to get it to SSD, so that way the lab works a little cleaner. There's less air in that procedure. So I will. So I don't have that dry mass, but I will have a moisture content of where it was at SSD. So you guys will have to do this to find that dry unit weight, or sorry, that dry weight. And again, the mass of dry weight is basically just equal to your mass of wet over 1 plus your moisture content. So that's all that is. Okay, so again, pretty straightforward. And if I did forget anything else, I'm 99% certain that Dr. Song has covered that in lecture. So as far as the lab report goes, again, course aggregate is extra credit. You don't have to do it, but it's a lot of copy and paste, and it's a good way to start the semester off right. There is a lab procedure example that one of my peers had written. It is not perfect, but it is really close, and it is for this exact lab. So that should give you guys a pretty good frame of reference for what to look at. Please look at the rubric as well. It's set up in such a way to be a lot of kind of free points. It's not meant to be super hard. I'll try to mark up your guys' lab reports a little bit more than I normally would, just give you guys more feedback. You guys are submitting them as a group, so please look at the Google Sheets and figure out who's in your group. All of these lab procedures are due on September 11th. And I think that is it. Your executive summary that's in there. The executive summary goes right at the top of the report after you have your title page, or you have your, I guess the way that you address that lab report. The executive summary, all that is I just want your final results. I don't need the data. I just want the specific gravity is this, the absorption content is this, the moisture content at SSD is this. That's all it is, nice and short. I'm going to give you my raw data sheet. I'm not going to do any of the calculations. I'll upload that as a PDF. Your job is to transcribe that and put it. You do have to have a table of your raw data in your lab report. So you do have to rewrite. Please don't take a picture of it or take a snip of it and put that in there. Please do all the calculations. For this lab, there's not a lot in general. For this lab, there is not there's no graphs that you need to make, but there is one table. So that table, and one thing I forgot to mention, I'll do real quick, is I mentioned that it's a standardized temperature that you need for specific gravity, and that's 20 degrees Celsius. I will measure the temperature of the water in my flask, and odds are it'll be 22 degrees, 19 degrees. It'll be something else that's not quite right. So what I'm really going to get is a GSP at T1. It's called T1 is equal to 21 degrees C. In the lab manual, and I believe there's the same table in the ASTM, or at least there should be one that you can look up. But in the lab manual, it'll have what's called an A table. In the A table, all it is a conversion factor. You do not need to calculate your own A values. Just pick one out and use it off that table. All you do is say you find the T1 variable. You'll have an associated A value, and it's going to be 1.003 or something similar. Okay, at T1. And all you're going to do is multiply A. That's going to equal GSP at T is equal to 20 degrees C. This is the answer I want. This is an arbitrary value that's close. This is your final answer that I'm looking for specific gravity in both the coarse and fine or soil specific gravity tests. So in the attachments, this is where you normally put any extra tables, any extra graphs, any images, anything extra that would go in there. The only thing that needs to go in the attachment section on this lab is a snip of that A table. Okay, it's the only extra thing you need for the attachment section on the rubric. If you don't have that, you won't get the points because it's not there. But that A table is the only thing you need. This is the equation on how to get it. So with that, we can start the lab. We can stop that.